Previously, we had considered the topic heat transfer mechanism on conduction and convection. Today, we are going to look at radiation. And of course, radiation is the transfer of electromagnetic wave or energy without any medium of propagation. The transfer of electromagnetic energy, electromagnetic wave without any medium of propagation. When I talk about electromagnetic wave, of course, I believe you know what I mean. A few to mention include the light energy, the infrared energy, and the ultraviolet radiation. When I say infrared, it's another name of heat. If I don't say heating effect, I can use the term infrared. The heat from hot bodies such as the sun reaches us by radiation. So if we have a body that is emitting radiation, the heat is being propagated through a process known as radiation. In this case, thermal energy propagates through space without a material medium. So if we are looking at a mode of transfer of energy in which energy or thermal energy is transmitted through the medium and the medium is a solid, we can say it's conduction. We use the term conduction. And convection has to do with the transfer of thermal energy of which the molecules or the fluid or the molecules of the fluid are also part of the motion. But in the case of radiation, this thermal energy is being transmitted and in this case doesn't require any medium of propagation. Let's assume we have a body that is emitting energy. Look at this. The rate in which thermal energy propagates is proportional to the surface area of that body, the foot power of absolute temperature, and the emissivity of the surface of that body. Okay, so when we talk about emissivity, it's just a dimensionless quantity. A body that has emissivity of 1 is simply referred to as an ideal absorber. If a body has emissivity of 0, then that body is simply referred to as an ideal reflector. What is an ideal absorber? An ideal absorber is an object that absorbs all the radiation incident on it. A body that has the potential to absorb all the incident radiation that falls on it. Such an object is called a black body. So you see a cloth that is black is an example of an ideal absorber, and it appears black in nature because it has absorbed all incident radiation. It can absorb all the incident radiation. It could be infrared, it should be visible light, it could be ultraviolet light. It has the potential to absorb the incident radiation, and you see it appear to be black at room temperature. A perfect black body has emissivity of 1. So a body that is a perfect black body has emissivity of 1. So an ideal absorber is also an ideal radiator of energy. So any object that has the potential to absorb can as well radiate energy. An ideal reflector is an object for which emissivity is equal to 1. An ideal reflector has an emissivity which is equal to 1. It does not absorb the incident energy, but rather it reflects all. So if I look at a cloth that is black, that is an example of an ideal absorber. A white cloth or a cloth that has the potential to reflect any light that is incident on it is an example of an ideal reflector. A white cloth is more comfortable to wear in the summer than the black cloth. In this area of our country presently that we are experiencing heat wave, it is advisable we wear material that has the potential to reflect away most of the incoming energy that falls on our body. So a black fabric acts as a good absorber of incoming sunlight and as a good emitter of this absorbed energy. About half of the emitted energy, however, travels towards the body, causing a person who is wearing the garment to feel uncomfortably warm. So white or colored clothes reflect away much of the incoming energy. As I've said earlier, the kind of clothes we wear can determine the amount of heat we want to come into our body. So if we wear a white cloth, it has the ability to reflect away most of the incoming energy. But the one that is black would rather absorb most of those energy, making us to feel uncomfortable. And of course, I have said that an ideal reflector has emissivity of 0, and I also said that an ideal absorber has emissivity of 1. Let's assume that we have a body, maybe a body is kept on this table and that body emits radiation. The body emits radiation and the temperature of that body is hotter than that of the surrounding. When that body emits radiation or temperature, it gets to a certain point or a particular temperature where the temperature of the body will be equal to the temperature of that of the surrounding. At that point, one would say that thermal equilibrium has occurred. Thermal equilibrium occurs when the temperature of that body is equal to the temperature of the surrounding. At that point, we can say that the net rate of radiation of a body, Q, is given by A E rho T to the power 4, where Q is the net rate of radiation of the body, A is the area of the body, E is the emissivity, rho is simply the Stefan-Boltzmann constant, the Stefan-Boltzmann constant, which is of the order 5.67 times 10 to the power minus 8, and T is the absolute temperature in Kelvin. So this expression could be used when the body has the same temperature with that of the surrounding. But in a situation where the body has a higher temperature, a different temperature from that of the surrounding, we can then use the expression here for the net rate of radiation. So we now write it as Q net equals to AE rho T to the power 4 minus AE rho T to the power 4 subscript S, where S is temperature of the surrounding. If we factorize this expression, then we get the second expression here. So they mean the same thing, and whichever expression we use will still give us the same value. Let's look at this example. I write the example 2 because we have already considered the first example in terms of heat conduction. This one says, if the surface or if the total surface area of the human body is 1.20 meters squared, because this is area, and the surface temperature is 303 Kelvin. So this is the temperature emitted by the human body. Option A says, find the total rate of radiation of energy from the body. The rate of radiation of energy from that body is what you're looking for. And we are being given, this one says, if the surroundings are at temperature of 20 degrees Celsius, this one is temperature in degrees Celsius, this one is temperature in in Kelvin. So of course we would convert this later. Question B says, what is the net rate of heat loss from the body by radiation? And then they now give us emissivity of the body to be unity. If the emissivity of the body is unity, it means that body is a black body as well, and we are going to take E as 1. Okay, let's look at the quantities given. So we now move to the next step, solving the problem. Solution. We are being given the area, 1.20 meters square, temperature of the body, 303 Kelvin. We have to find Q. And the temperature of the surroundings, 20 degrees Celsius, which we are going to convert by adding 273. And it now gives us 293 temperature of the surrounding in Kelvin. Emissivity is 1. The Boltzmann constant is given as 5.67 times 10 to the power minus 8. Okay, so we have to find the net radiative energy transfer from the body and the total rate of radiation of energy from the body. Of course, we have to pick an expression suitable to solve that problem, and of course we go with this Q equals to A E rho T to the power 4, where this T here represents temperature of the body, and we are to find the total rate of radiation of energy from the body. So the rate in which energy radiates from the body is given by this expression. Other quantities are given, I've listed or mentioned them, so I wouldn't like to spend more time. Of course, you see A here, look at it here, and emissivity is 1 here. Stefan's Boltzmann constant is given here, and the temperature of the body. So when we substitute the following, we now see this. When we simplify, we get 547 watts. So Q is given as 547 watts. Let's go to the next question. The net rate of heat loss from the body. The net rate of heat loss from the body, we're going to use the expression A E rho T4 minus T4 subscript A. So this will tell us the rate in which energy flows from the body to the surrounding. Okay, so we are going to substitute the values for A, E, and rho, and then the temperature of the body and that of the surrounding. If it is positive, then energy flows from the body to the surrounding. And if it is negative, then it is the reverse. So when we substitute the values, of course we have this, and then simplify it, we get the final answer to be 72 watts. So the rate is positive because the body is losing heat to the surrounding. I think we have come to the end of today's class, and I would like you to give us a thumbs up, and also if you know you have not subscribed to the channel, do encourage us by clicking on the subscription button. Thank you very much, and I would like to see you in our next class.